Okay, guys, so the first practice problem is basically this one, which they said is an air compressor of mass 200 kilograms with an unbalance of 0.01, but this information, as we discussed, I don't think is needed, is found to have large amplitude of vibration while running at 1200 RPMs, okay? Determine the mass and spring constant of the absorbers to be added if the natural frequency of the systems are to be at least 20% from the impressed frequency, okay? So just like I mentioned before, before we're doing the problem, I think this problem is about, this type of system. This is the original system, M1, K1, and now the system you're gonna add is the M2, K2, okay? So what they're asking you to find is for the conditions given on the problem statement to find M2 and K2, okay? So first thing to do would be to do some type of figure like this one. So if you ask me, that's what I would do. I will say, okay, this is my M1. This will be my M2. It will be the K2. You can do a better figure than me. This would be the K1. Okay, and now what we know is what? We know that this over here vibrate at a frequency of 1200 RPMs. And what else do we know? M1 is equal to 200 kilograms. And they ask us that if the natural frequency of the systems are to be at least 20% from the impressed frequency. Okay, so natural frequencies. At least 20% higher than, I put it over here, but I'm guessing it's omega 1, comma, capital omega 2. So basically, as we said before, okay, I think this is important over here, is that basically what I want to do is just do a little figure like this one over here, kind of, I don't know if it's exact or not, but to show what, like the original system with just the mass M1 and K1, original system with just the mass and K1, you have basically this. Okay, I don't know if it's going to be like that or not. Okay, this is just M1, K1. Now, what happens when you add the absorber? We're going to get two frequencies. That will be these two over here. So this is the ratio of capital omega over omega n. And this is, doesn't matter, this is x, matter the amplitude. And basically we're gonna get one peak over here. I'm gonna go all the way down. And another peak over here. This is gonna go all the way down as well. So basically, doesn't matter the figure is not exact. What's important here is to realize what is that this over here at this location, what we're gonna have capital omega 1 over omega n according to the figure, and at this location right in the middle, we're gonna have capital omega 2 over omega sub n. By now we need to find out what is the omega sub n here. I guess it's the omega sub 1. All right. So what we can see over here is that, the equation of motion for the system, again, you don't need to redo the whole derivation. You can just copy from the solutions, but you can say solution math. So the solution of this system, so you know exactly what's happening, will be of which form? This one here. So you can copy this equation here. M1, 0, 0. M2, x1, x2, plus K1 plus K2, minus K2, and I guess it's K2, no? So basically, this is what I just copied, the same equation. And you can say here, assuming solution x sub I equal x sub I e I omega t. So you show me that you remember the procedure, and substituting into equation of motion. What do we get? I mean, this is what I would like to see on an exam. See, I don't ask you to do all the derivations, but at least that you show me understanding. So this is what you say, blah, 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 blah. Actually, you could also add the one of the force if you want, and F equal capital F E I omega t. So basically, I just added this one here. You don't need to copy all this stuff. Okay, I'm not going to ask you to do the characteristic equation, then solve, use the impedance. If you want, you can do it, but we're going to say, I'm going to write these equations, okay? So let's say we're going to get x1 equal to that long equation there, 1 minus capital omega, omega n square x static. Really what I'm interested is about the denominator, 1 minus 1 plus mu omega n over omega sub a square minus capital omega omega sub n square times 1 minus capital omega omega sub n square minus mu sub n mu sub a square. X2 is x static divided by the same thing, basically. 1 plus mu. Where I can go to the pages, I'm going to recopy what I just wrote. Sorry, this is not square, this is omega 2, okay? On the figure, capital omega 2. All right, so now, as we discussed before, what is what I'm going to try to find is what is the ratio of this frequency of just the capital omega at these 2 points over here. Okay, so in order to do that, what do we know? The amplitude here of the x will be infinite. So when is that going to happen? When the denominator here is 0, no? Okay, so let's say the amplitude of x1 and x2 are very large when the denominator is 0. Okay, so that means that we have 1 plus mu omega sub n over omega sub a square minus capital omega over omega sub n square times 1 minus capital omega over omega sub n square minus mu omega sub n over omega sub a square. Did I forgot a bracket here? No, looks like so. All right, so over here, also the maximum vibration generally happens when? At resonance, no? So what happened at resonance? That the natural frequency of this system, so assuming that this mass moves with this mass, yeah, would be resonance, no? So what would that mean? So at resonance, which means what? The ratio of omega, so it will be omega sub n equal to omega sub a. This ratio will be equal to 1. Does that make sense or no? Yeah, that will be resonance. Okay, so let's go and substitute into this equation. Let's see what happens. So let's say here, equation star. Yeah, I don't know why I started to write on this page, but it's fine. I'm just going out to this page now. So we can say equation star becomes 1 plus mu minus capital omega over omega sum n square times 1 minus capital omega over omega n square minus mu. Sorry for that. Minus mu equal to 0. So basically from the notation here, I needed to be careful how to zoom in. This is look like n, this is a, n, but I think I should redirect these ones to make sure that, and this one is omega sub a as well, no? So I think all of them should be the same. So we have a here, so maybe change this one also by a and a on top. So it should be a, and and that's it. Okay, so basically at the end what we have is this over here. This equation over here. And what are they telling us on the problem statement? Is that determine the mass and spring constant of the absorber to be added. So mass and spring constant of the absorber to be added in the natural frequencies of the system. So which are the natural frequencies of the system? Capital omega 1 and capital omega 2, no? Yeah. All the systems are to be at least 20% from the impulse frequency. So what does that mean? If, let's say, capital omega over omega absorber needs to be higher, but let's say equal to what? 20% will be 0.2, no? Oh, wait, that would be, yeah, that would be 0.8. Hold on 1 second. Needs to be at least 20% from the impulse frequency. So this would be 0.8, no? Instead of 0.2. What it's meaning is that then the ratio needs to be at least 0.8 instead of 0.2. To be this frequency here, capital omega, needs to be 20% of the natural frequency of the absorber, no? Of the system. Because what did we assume? This, no? Yeah. So under this condition, so if you want here, solving. So now what does that mean? If we go, what would be the only unknown? Would be mu, no? So solving equation double star for mu, which is what I did on Maple. Basically what I did is all this stuff in Maple. Let's look at it again. I wrote the equation here. Maybe I need to change it. This is omega sub A. Omega sub A. According to the notes. So now I get this equation here. I did the substitution of omega sub A is capital omega. I mean, you can do this is equal to 0.2. Will be the 0.8. But with this, I'm not able to do it, okay? So if we solve for this, what you get is mu equal to 0.2025. And we know that by definition, mu under this notation is what? Is M2 over M1. Where M1 was the mass of the system over here. So now we can solve here now for M2 will be equal to mu times M1, which is basically 0.2025 times 200. And this, once you do the calculations, will give you M2 equal to, I think it was 40.5, but let's check over here. No, yeah, 40.5 kilograms. Okay, and finally, what do we know? What would you know over here? Okay, so that the omega would be of the absorber, our resonance would be equal to this, should be equal to K2 over M2, which will give you that K2 will be equal to the capital omega. No, but we're already introducing to find the mass. Now for this mass, we're going to find out what is the value of this. We're always going to take in twice the effect of the 0.8, no? This will give you the capital omega times M2. So you do this will be what, the 40, so K2 equal to, I think we had, oh, I did on here on the Maple, I didn't on the solution. They give us the frequency in 1200 revolution per minute. If you transform that into radians per second, what do you get? 40 pi. Okay, you multiply by 2 pi, you divide by 60, you get 40 pi squared times 40.5. And this should give you a K2 of 639,550.3654, and that should be newtons per meter.